Now today we're going to take this whole idea of combustion analysis to determine an empirical formula, and we're going to ratchet it up a notch. A lot of times when you go through combustion, I think we learned in a previous chapter that what you're going to produce is carbon dioxide and water. And we're going to, especially if you burn a hydrocarbon, something like a fuel, and so that's what we're going to see in the problems we're going to work today. The problems that we're working today, they are going to tell you are specifically only containing carbon and hydrogen. So what we're doing today only works if it's only carbon and hydrogen in the compound. Now, he does go off at the end of the section and explain what you're going to do if you've got oxygen involved in it as well. I'm not going to give you any problems like that today. Today, we're only going to worry about problems that have just carbon and hydrogen in them. So that other little piece of explanation, you don't have to worry about it quite yet. We'll take care of that in a day or two here. Okay, so if you look at the sample problem that I'm going to work for video number 5, it says a compound containing only carbon and hydrogen is burned in a combustion analysis experiment. And he shows you a really nifty picture in the book of how they actually do this, where they take those combustion products and they actually have everything sealed off, and they have one compound that is going to collect all of your water, and then they have another compound that's going to absorb all of your carbon dioxide. Then you can do a mass difference and figure out how much of each that you have. So that's where those numbers are coming from. Okay, so we're burning 1 gram of the compound. We're producing 3.14 grams of carbon dioxide and 1.29 grams of water, and we want to know the empirical formula of the compound. Now, what you have to realize here is that because it only has carbon and hydrogen in it, the carbon is only going to go to one place. If it's producing carbon dioxide and water, all the carbon's going to go into the carbon dioxide. If it's producing water, all of your hydrogen is going to end up in the water, because water doesn't contain carbon, and carbon dioxide doesn't contain any hydrogen. So if I have those two compounds, I can figure out exactly how much carbon and how much hydrogen I had in my original compound. So let me show you how to do that. They tell you that you produced 3.14 grams of carbon dioxide. And you probably already know, the first thing we have to do is we have to convert that to moles. So for every 1 mole of CO2, I'm going to have 44.01 grams of carbon dioxide. So this will cancel out, and that tells me that I'm going to have 0.0713 moles carbon dioxide. So if you divide that out, and that's the number you should get. Okay, now, for every 1 mole of carbon dioxide, I also have 1 mole of carbon, because the subscript here is 1. So what that tells me is that if I have 0.0713 moles of carbon dioxide, I'm also going to have 0.0713 moles of carbon. Okay? All the carbon in the compound has gone into the carbon dioxide, so I know that that's how many moles of carbon were in the sample that I burned. All right, now let's move on to the water. I have 1.29 grams of water. Okay, for every 1 mole of water, I have 18.01 grams of water. That's the molar mass. Okay, I'm sorry, 18.02. If you say hydrogen's 1.01, you're going to end up with 18.02. Okay, so your grams of water will cancel out, and I'm going to have 0.0716 moles of water. Okay, now, going to have to be careful, because up here, the ratio of carbon to carbon dioxide is a 1-to-1 ratio, because the subscript for carbon and carbon dioxide is 1. In water, I'm looking only at the hydrogen, but this subscript is 2. So therefore, if I know how many moles of water I have, that's going to tell me I have twice as many moles of hydrogen, because there are 2 moles of hydrogen in every mole of water. So if I take 0.0716 and I multiply that by 2, that gives me 0.1432 moles of hydrogen. Now, just like I did the last time, I now have a ratio of moles of carbon to moles of hydrogen. Okay, here's moles of carbon, here's moles of hydrogen. I want the simplest whole number ratio, so I'm going to look at these two numbers. I'm going to say which one's smaller. Okay, this one obviously is smaller, so I'm going to divide everything through by this number. And when I do that, I will end up with 1 up here. And if you take 0.1432 divided by 0.0713, you're going to come up with 2 down here. And so therefore, your empirical formula here is 1 mole of carbon for 2 moles of hydrogen. So the empirical formula is CH2. Okay? So again, all we're doing is saying if I know number of moles of carbon, number of moles of carbon dioxide, I can convert that to moles of carbon. If I know moles of water, I can convert that to moles of hydrogen. Since those are the only 2 elements in the compound, once I can divide through and take the simplest whole number ratio, that will give me the number of moles of each one in the compound, which is the empirical formula.